So in this video I'm going to talk to you about intermolecular forces of attraction. We've already looked at intramolecular forces of attraction, and the difference between them. Intramolecular kind of refers to within a molecule or a formula unit. So good examples are covalent, which involves sharing of electrons, the ionic bonding, which involves transfer of electrons, so that's an electrostatic attraction, and then metallic bonding, which involves electrons kind of delocalized, so they're moving between orbitals of different metal atoms, and the nuclei are all kind of in the middle. So those would be within molecules or within formula units. Intermolecular refers to between different molecules. So examples of those, we have hydrogen bonding, dipole-dipole bonding, and these two are actually very, very similar. There can be different exceptions, but very, very similar. And also van der Waals forces of attraction. They're also called London forces of attraction, but we'll call them van der Waals because it sounds better. So the definition of hydrogen bonding is when you have the hydrogen atom of one molecule is attracted to a highly electronegative atom on another molecule. So the highest electronegative atoms are fluorine, oxygen and nitrogen. So a really good example of hydrogen bonding is in water, H2O, and I'll draw it out in a second. Dipole-dipole, when we've looked at electronegativity and polarity, this would be the attraction between two polar molecules. So again, it's very similar to this one, but this one's more specific to hydrogen. And this one can involve lots of other different atoms. And then van der Waals is called an induced dipole, which I'll talk about. It's better to use a diagram for that one. Alright, so let's look at hydrogen bonding. I'm going to erase this. So the idea of hydrogen bonding is when you have a polar molecule, and H2O is very polar. So the electrons are all being pulled towards the oxygen because it's highly electronegative compared to hydrogen. So what we have is a dipole. So we have the possibility that another molecule can be attracted to another one. So this negatively charged area on the water molecule can be attracted to the delta positive charge on another, and then this can continue. I could keep going forever and ever, but I'm not going to. So the idea is that each molecule is strongly attracted to another one, and this property of water helps explain a lot of its chemical and physical behavior. So it's got a very high boiling point, 100 degrees Celsius. The idea of water expanding when it freezes rather than contracting, snowflakes, right, is all to do with this property of water, which is hydrogen bonding. So again, the definition is when you have a hydrogen atom on one molecule and it's attracted to a highly electronegative atom on another molecule, and the best example is H2O or water. So that's that. We'll use a slightly different example for the dipole-dipole interaction, so one without hydrogen. So let's use this molecule that I've just made up. So the difference between electronegativities of the carbon and chlorine means that this chlorine, or these chlorines, would be delta negative because the electrons are all being pulled towards that atom, just off lone pairs. So there's a delta positive area, delta negative area, so a dipole. So remember, a dipole is when you've got negative area, positive area, so it's a polar molecule. So in this case, this area of the molecule could be attracted to this area and another molecule. So very, very similar to hydrogen bonding, but just can involve lots more atoms, and hydrogen bonding is obviously specific to hydrogen. So dipole-dipole is when you have polar molecules attracted to each other, and that's an example. So the van der Waals forces is the weakest. Actually, I didn't mention that earlier, but the strength of these goes this way. So hydrogen bonding will be the strongest, and then it goes down this way. So van der Waals are very weak, but they are present. So the idea of an induced dipole And let's look at nitrogen as an example, or N2. So if we looked at electronegativity values, even just common sense tells you that this would be non-polar because these two atoms both have equal numbers of electrons and protons and everything makes them the same. So the electrons will be perfectly shared in the exact middle of these two. But the idea of an induced dipole is the electrons are moving. So they're around each atom, but they're also moving kind of very close to each other, maybe overlapping at some point. So there's a very good chance that even if it's just for a very small amount of time, one area could have more electrons and one area could have less. So in that case, then you could have a dipole. So you could have this dipole. So you could have this, could then induce a dipole on another molecule. So electrons are moving around, lots of energy randomly moving within a certain energy level. Then electrons can spend a little bit more time with one atom as opposed to the other, which can then force the electrons, kind of repel them electrostatically, so this ends up, whoops, as delta negative, and that ends up as delta positive. So this happens, and then it causes another dipole, and then you have this very weak attraction between two molecules. So this, I mean, if this can exist in a molecule of nitrogen, which is N2, so the atoms are sharing the electrons perfectly, then it can happen in a lot of different non-polar molecules, even if it's the same, if it's a diatomic element such as this. So hydrogen bonding, strongest, then dipole-dipole, polar molecules, and then this induced dipole or van der Waals forces of attraction would be the weakest. And that's it.